Yeah. Okay. All right. Thank you all for being here this afternoon. I'm Robert Mahoney, the mission manager for Neurospace, and today I just want to give a bit of an overview of our company, some of the key technologies we're developing in our flagship product called HiveR, and why we've made some of these design decisions. So who is Neurospace? We're a relatively young new space and robotics company that was founded in 2020. Our CEO, Irene Selvanathan, has a history working for new space companies, most notably ExoLaunch, and we have a team that's got a fairly diverse range of backgrounds from engineering. I myself studied hypersonics at university, worked as a structural engineer at a rail company, worked as a certification engineer at a drone startup, and also while doing that, moonlighted as a Mars colony designer for fun, as you do. So why the moon? Well, mainly because it is a fantastic stepping stone to Mars. I know we've spoken a little bit about this today, but just quickly, Mars is one of the most interesting places in the inner solar system. It's got a history very rich and similar to Earth's, and so it's one of the best places to explore looking for life. So why not just go straight to Mars? Well, unfortunately, Mars is a lot further away than the moon is, roughly 200 times the distance. Launch windows open up every 2 years rather than every 3 days. It takes you about 9 months to get there, and there's enough of an atmosphere to be a pain, but not enough to be useful. In addition to this, there are a lot of companies and governments that are already making a push to the moon. So a lot of the infrastructure for getting there and communicating is also being solved. So what is the moon like? Well, due to the lack of a magnetosphere, it's incredibly radioactive, roughly 3 times as radioactive as low Earth orbit, I believe. It has a 14-day day-night period, and the temperatures range from almost 400 degrees Kelvin down to almost 90 degrees Kelvin on average. The surface regolith is an incredibly destructive substance because it is essentially a series of small daggers. And because of the lack of atmosphere, it tends to stick to everything. That having been said, it's not impossible to solve the problems. We've done it before. We can do it again. The first was Lunokhod in 1970. This was much larger than what we're looking at developing and was able to use radiothermal heating to keep it warm during the night. Now, this isn't a lunar rover, this is the Sojourner, but it's much closer to the scale we're talking about. Most interestingly here, with a 15-watt solar panel, it was able to travel over 10 kilometers in its full operational life. And more recently, you've got the Chinese rovers Yutu-1 and Yutu-2, which are much more similar to the original Lunokhod. Now, all of these just give examples that this technology does exist. We can use it, even though it is hard to overcome some of the design challenges. So those are some of the basic design requirements and things we need to consider. How can we go about this in a way that makes sense from a financial standpoint? Well, one way is to potentially look at what's worked in the space business in the past, specifically CubeSats. Now, CubeSats are a standard that, as the name suggests, is a 10 by 10 by 10 centimeter cube based around what is called a 1U. These individual volumes can be strung together to make, for example, a 3U satellite, which is one of the most used versions. And these were originally developed in the late 90s and early 2000s, and at the time were considered basically toys for university students to help them develop the skills to work on proper satellites. Now, however, they are the corner of billions of dollars of industry. They have been used for everything from Earth observation to testing out solar sails and space station orbits. And while the commercial industry has taken over as the primary user of them, they're still heavily used within university programs. I believe one of our partners, TU Berlin, actually has the distinction of having the most satellites of any university in orbit. So how do these compare with where rovers and that sort of technology is now? Well, as it stands, you can go online and buy anything from thrusters to communications equipment to launch services, all in a very standard and open design spec sort of way for CubeSats. There are dozens of launch companies, there's dozens of different ways of solving all these problems, and they're relatively cheap and all off the shelf. Rovers, on the other hand, and this is partly because they haven't had 20 years of development, so we can forgive it for that, tends to be fairly, all the designs are bespoke, they're all unique, and they're all very, very different, and as a result, expensive. The main downside of this is that a lot of people who want to develop these rovers to help explore on the moon have to spend a lot of time worrying about all the other systems. And even if some of the more developing designs are used, they're still very restrictive in what you can do. So you've got a lot of limitations on your design process, so you can't focus on your experiment or your application. So our concept is very simple. You take a basic 3U CubeSat, you build a chassis around it, and then you make it moonproof. Simple, right? Now, obviously, it's a little bit harder than just slapping a chassis and a few motors onto a CubeSat. But what this approach will do is it allows us to tap into this existing market of components, and it gives us a lot more flexibility to focus on the things that haven't been developed, things like the motor control systems, the thermal systems, and the communications. Come on, there we go. So as some examples for applications, this will allow people to focus, like I said, more on the experiments. You've got potential applications for pharmaceutical and biological experiments. The unique gravity on the moon could be of particular interest. Essentially, what you could do is go to the moon, deploy one of these, drive a certain distance away, and then run your experiment in lunar gravity. You can also, there's obviously also the applications for mining and investigations of the material composition of the moon. However, given the size of these things, you're not exactly going to be doing large-scale mining operations. That having been said, they can be very useful for prospecting and taking samples and analyzing them. So that's what you can do on an individual basis, but we are looking at ways of making these network together, hence the name HiveR. Basically, because of the simple, small, and standardized way, we envision that these can be deployed in swarms with certain rovers being used for specific tasks. So, for example, you could have a queen rover that is the main communication hub designed to communicate back to either a lander or a low altitude satellite. You could then have drones specifically designed for photos and analysis, and then workers designed with robotic arms in order to be able to manipulate things on the surface. And one thing we are working on a mesh communication network that all of these can use in order, so even if a drone has completed its task or possibly broken down, it could still act as a communication hub. Yeah. So in order to help with with people developing their individual missions and examples, we don't actually, we found that, you know, developing a space grade motor is incredibly expensive. And if you want to do experiments here on Earth to make sure that your system works, you don't necessarily need to shell out all that money. So as a result, we are developing a tiered approach here where we will have progressively higher and higher degrees of qualification and cost associated with things. What we hope this will allow people to do is that they can take the cheaper components, which aren't necessarily as robust, but have the same size and form factor and communication protocols, but then use those to help to run, you know, experiments and tests, possibly in a university environment. And then when time actually comes to launch a mission, then you can buy the expensive stuff and don't have to worry about breaking it while you're doing the testing. So, like I said, this is the approach we're going for. And if we're developing an academic rover and we're developing a moon rover, there's also a bunch of crossover in the middle there. Obviously, components that can operate on the moon need to be able to survive in a highly radioactive and either high temperature or low temperature or both environment. This allows certain rover components to be developed that can work in more harsher environments here on Earth. So we've also been looking at a couple of other components that would be nice to haves, not necessarily need to haves, specifically our robotic arm here, HiveR Flex. This is designed to be a robotic arm that can fit within a 1U component. And again, that we're going to try to offer this in various degrees of complexity and qualification. So that's essentially the system we're trying to develop here, one platform that can be used, that can be not only standardized, but also used across a degree of qualifications and thus applications. We've already done a fair degree of testing with our academic rover here at DFKI earlier this year. And this is our original prototype that used a slightly different suspension system, a rocker bogie rather than what you saw previously. We moved to this newer suspension system as it was a bit more compact and lightweight, but this still allowed us to develop some of the control systems and the wheels. Now, this is particularly interesting because this rover was being controlled not from Europe or even not from Germany or even Europe, but from the United States. We've developed a protocol that allowed people over the internet to just dial into the rover and to drive it around. And we're going to be using this on July 20th at Moon Day, where we'll be throwing a big event allowing people from around the world to dial into our rovers and drive them around at certain locations. Okay, all right. Thank you very much for your time.
Thank you, Rob. No problem. Thank you for the nice presentation and a short overview of Neurospace and its activities. Questions for Rob?
Hi, Rob. Thanks a lot for the presentation. I just have a question about some of what time scales, right? Like some of the components that we often have access to for CubeSats don't have the same qualifications as some of the things that we need for a Mars mission, right? Is Neurospace also looking into improving off-the-shelf CubeSat components so that we can use it on this type of rovers?
So our intention is to start off by validating what already exists. So just because a lot of the computer components, for example, haven't been run in lunar levels of radiation doesn't mean they can't be. And then if it turns out that they can't be run in that, we'll then look into developing more complicated ones, ideally keeping the same form factors and sizes.
Pretty cool. Thanks.
Very interesting idea. Just quick question. So you mentioned about academics. So your rover concept, does it has only wheels, or is there any chance to customize those kind of things? Maybe put like a bipedal robot or something, maybe try to include some kind of locomotion from research perspective. Is there any way to do that? So or it's like only wheel rover concept?
So is your question, are we only focusing on wheeled rovers? Or
yes.
Currently, we are only focusing on the wheels there. They're been designed in partnership with TU Berlin in order to be able to better move through the lunar regolith. Obviously, we could change the wheels out for something else, but right now we're just looking at wheeled designs.
Okay, thanks.
Any other questions? Yeah. Thank you.
You spoke about the importance of standardizing the cube rover formats. What steps do you see your work going towards it? Like, are you guys contributing towards the development of such standards so that university students could pick that idea up as well and use that as a guideline or stepping stone?
Well, our first step is obviously to start off with the CubeSat as the basis and build out from there. We intend to make the physical components as open source as possible. Obviously, we do need to take some steps for intellectual property protection, and also same with the software, but we are open to working with universities and letting them customize or develop stuff as much as they want or desire. Again, the idea is to make this as open source and as accessible as possible. So if people want to, say, develop a different locomotion system, but have But once we've developed, say, a thermal protection system, then we can make it a little bit more as interchangeable as possible. Obviously, we can't make it infinitely interchangeable, but
I could feel you see any applications for
Okay. Oh, sorry, the online users always forget. Do you see any applications for using on the outer shell of the ISS or gateway or those types of options, given that it's already certified for those?
sorry, could you repeat your question? I didn't quite hear you.
Sorry, for the rover, do you see any applications for it to be on the external shell of ISS or gateway?
We haven't actually considered that, I'll admit. One of the problems with being on the outside would be how to make sure it stays affixed. We'd have to have a very unique system there, given that they're mostly either aluminium or like Kevlar fabrics, I believe they're looking at. So you couldn't just use magnets. I'd love to just use magnets, but no.
Yeah, thanks for the interesting talk. One question I had was we heard that low Earth orbit and lunar and Martian is quite different from radiation perspective and atmosphere and thermal management. And so the question is, are you designing the early phase Tier 1, Tier 2 motors in a way that you would be able to swap them for motors that would be able to withstand the radiation? And for example, if you don't have an atmosphere, you have to take a maybe total different approach to thermal management in these motors. So you will not be able to swap them for the same form factor, just saying, okay, now I need Tier 4 and it's just more expensive, but it won't be the same motor at all. Maybe you or what is your take on this?
Our goal is to make them as interchangeable as possible. That might result in the terrestrial motors actually having a bit of dummy space on them in order to make up for that, but still essentially having that same fit, essentially a smaller motor inside a shell that makes it resemble the larger motor. So,
yeah, thanks.
Hello, amazing idea, not gonna lie. So
thank you.
in terms of university students and everything, how do you plan or what kind of platform do you intend this specific rover to be on?
Sorry, can you just repeat the question?
So for the rover to get on the surfaces, what kind of platform do you intend it to be on? Does it require special deployment sequences, deployment platform, or do we have already? Are you going to provide this infrastructure or something like that?
We are currently, we're just focusing on the design of the rover itself. Our intention is to try and make it as androgynous as possible so that you could fly it on a Starship or you could fly it on an astrobotics lander itself. So we want to try and make it as flexible as possible in that respect.
Thank you. And again, on behalf of the organization committee and all the committee members across the room, I'd like to thank you for sponsoring the Hermes workshop as well.
Oh, no
so we appreciate that. Please join me thanking Rob for his presentation. Thank you.